This is the lecture number 30 of the Smart and Microsystem course, where we would be studying about the formulation of finite element for the smart material structures, and in this case we are considering piezoelectric material structures. So, in the previous lectures we basically started studying about the finite element formulation in general, taking mechanical system into the basic aspects of finite elements for mechanical structures. And in this lecture we would basically be extending this to smart material structures, and typically although there are many materials, as we discussed in our earlier lecture, piezoelectric material structures is considered for demonstrating the finite element method for such structures. So, just to introduce, we studied that in the initial lectures, that smart materials typically like the magnetostrictive material like terphenol or the piezoelectric material like PZT has two constitutive law. One is the sensing law and the actuation law. So, it is this two laws give rise to, in addition to the mechanical component, there is also an electrical component. The additional complexity arises in the finite element formulation. So, this additional complexity is due to the coupling that couples the mechanical energy to the electrical energy. So, what does this mean in the finite element terms? It introduces additional matrices. So, here we have given two laws where the sigma is the stress is related to the mechanical part, C is the stiffness, which is basically material properties, and epsilon, which is the strain, and the electromechanical coupling coefficients E, that is what we call the piezoelectric coefficient, which is coupled to the electrical field. And here we have said that the mechanical stress is a 3/1 vector for a 2D problem, that is sigma x, sigma y and tau xy, and the 3/3 is the material property matrix, and epsilon is the 3 strains corresponding to the stress, that is epsilon x, epsilon y and gamma xy, and the 3 electric field in the and the 2 electric field in the 2 coordinate direction Ex and Ey. Similarly, the electrical displacement D is related to the strain through electromechanical coupling coefficient, piezoelectric coefficient, and the permittivity of the medium and the electric field. So, this is the first is an actuation law, second is the sensing law. So, in the above expression, E is essentially the matrix of piezoelectric coefficient, which has a unit of Newton per volt millimeter, and it is of the size 3/2. And the electric field is basically in the 2 direction Ex and Ey, which is related to the voltage and the thickness of the structure. T is the thickness of the structure. Vx and Vy are the voltage in the 2 directions, the coordinate directions, applied voltage. And the electric field has the unit of volt per millimeter because it is V/T. T is in the thickness in the millimeter. Mu is a permittivity matrix of the size 2/2 and measured at constant stress and has a unit of Newton per volt. And D is the vector of electrical displacement, which has a unit of Newton per volt millimeter. So, the C basically is the mechanical constitutive law, which we already said what it is in our previous lectures in finite element, and the above constitutive law can be rearranged by taking the epsilon on the left hand side and S as the compliance matrix, which is nothing but C inverse into sigma, and D matrix is the electromechanical coupling coefficient into E, where D is equal to C inverse into the piezoelectric coefficient matrix. So, where the coupling matrix, that is D, has a unit of millimeter per volt because it is taken in inverse here. So, in most of our analysis it is assumed that the mechanical properties will change very little with the electrical field, and as a result we can uncouple both the sensing law and actuation law which is not true in the case of magnetostrictive material. It is highly coupled, but in the case of piezoelectric material it makes our life little simple, mainly because these laws can be uncoupled because of the behavior that the mechanical properties change very little with the change in the electric field. So, the first part of the equation, that is the actuation equation, represents the stress developed due to the mechanical load, while the second part is the same, gives the stress due to voltage input. So, we have that epsilon equal to S sigma plus d into E. So, the first part is because of mechanical and the second part is because of the electrical field. So, it is clear that the structure will be stressed due to the application. Suppose we do not have a mechanical loading, and if we pass an electric field, we see that it is going to be stressed or strained, and the vice versa. Suppose we apply an electric field, it will be stressed, so it will also elongate. That is what, alternatively, when the mechanical structure is loaded, it generates an electric field. So, this is what we call the smart concepts. So, we can actually use these aspects of the additional terms that are coming to our actuator application or sensing application. So, I have said that, in other words, the above constitutive law demonstrates the electromechanical coupling, which is exploited for a variety of structural applications involving vibration control, noise control and health monitoring. So, now let us talk about actuation. So, as I said, when we pass on the electric field, the mechanical structure elongates, causing the strain. So, in this respect, let us consider the structure shown here, which has a length, width and the thickness in this direction. And let us consider two thin piezoelectric electrodes which are placed on the, which are bonded to the top and bottom surface, and such a structure is called the bimorph structure, and here we have taken a bimorph plate of thickness T, this is the thickness T, having length L and width W. And now suppose we pass on an electric field through a system here where we pole it this way. When we pole it, basically we will have the strain developed in the direction perpendicular to the poling direction. So, this is the direction of poling. So, if in the current position it is shown, we will have a stress in this x direction and also in this direction, which are the perpendicular direction to the poling field. So, when we do that, so we can actually relate the change in length, that is the strain, to the D31. This is because the 3 says that it is in the direction 3 with the applied voltage in the one direction. So, we are actually poling it in the third direction and we are getting the stress in the one direction. So, that is why we have D31, and E1 is the electric field and L is the length. So, this is basically D31 VL by T is basically the strain in the length direction, and D31 VW by T in the width direction, and in the direction of poling it is D33 into V. So, we know that if we can actually pole in the appropriate direction, and we can actually pole in the direction, if we know in what direction we want the stress or strain, we can actually pole the piezoelectric plate in the appropriate direction. So, as I said here D31 and D33 are the electromechanical coupling coefficients in direction 1 and 3 respectively. Conversely, if the force F is applied in any of the length, along any of the length, width or thickness direction, the voltage V that is applied will be D31 F by mu by L, that is coming from the second constitutive law, where mu is the permittivity of the medium. So, it can be in the x direction it is D31 F by mu L, D31 F by mu W in the W direction, and D33 F by mu L W is in the thickness direction. The reversibility between the strain and voltage makes the piezoelectric material an ideal for both sensing and actuation. So, we will actually see how we can do as we go along in this lecture. So, what are the piezoelectric types? We did discuss this in our earlier lecture, that is our lecture number 2, where we said there are different kinds of piezoelectric material and it is available in different forms, either in the ceramic form or in the crystal form or in the polymer form. The most commonly used is the ceramic form, that is PZT, where PZT stands for lead, zirconate and titanate material, which is extensively used as a bulk actuator material, as they have high electromechanical coupling coefficients. Here we are talking about D31 and D33. So, the material which has very high D31 and D33, we call it as a very good actuator material. However, the polymer form of the piezoelectric material, which is called the PVDF, that is PVDF is polyvinyl difluoride, which has a very low D31 and hence extensively used as a center material. It cannot be used as an actuator material. And we also talked about the other forms of the piezo material. It is in the form of fiber composite, the piezo fiber composites. Basically, it is used extensively as an actuator material because it can be embedded into a composite structure, and it is found that it is very useful to do vibration and noise control. Here we would not be talking about PFC here, but we will see how the same constitutive law can be used for PVDF and PZT material and how it can be used for sensing and actuation application. So, now coming back to the finite element modeling. See, the finite element modeling of the mechanical part, which is epsilon equal to S times sigma, is very similar to what we discussed in the previous lecture, except that the coupling terms introduce additional energy terms in the weak form of the governing equation, which would result in the coupling matrices in the FE formulation. So, what does it mean in the finite element modeling? So, the introduction of piezoelectric material introduces an additional degree of freedom, which is in the form of the electric field E. This additional degree of freedom can be an electric potential phi, which is related to electric field E by taking the gradient of the potential phi, or we can take the electric field itself. Either way it is fine. Alternatively, since the sensing and actuation law are not coupled, analysis can be performed by using conventional beam type elements or plane stress type elements or even plate element derived earlier, and the effects of coupling terms are translated into equivalent loads, concentrated loads onto the beam structure, and the conventional beam element which we actually used can be beam or plate element or plane stress element we use can be used to actually solve both sensing and actuation problem. We will deal with these two and see how each of them can be used in this lecture. So, the first approach we call it as the lumped approach, where we are doing an FE analysis of a piezoelectric bimorph beam. So, here there is a bimorph beam where there is two layers, one is the top layer and the bottom layer are stitched together, and we have taken 100 mm by 0.5 mm by 0.5 mm, 5 mm by 0.5 mm, the width is 5 mm. So, here the two bimorph beams are stitched together, and we consider this bimorph material is made up of polymer type of piezo material, that is a PVDF beams with opposite polarities. So, the PVDF patches are poled in such a way that the strains are produced in the axial direction, that is we pole in the YZ plane, that is in this direction, so that we get the stress in the x direction due to the applied field in the z direction. So, we get the field in the z direction. So, we get the poling in z direction will introduce a strain in the x direction. So, these are the dimensions. So, what does it mean if I use a lumped approach? So, this is going to cause a force F at this end and a force F in this end, which is basically equal to a couple. So, we can actually calculate this force from the piezoelectric constitutive law and apply a couple to the cantilever beam and then study the response using our beam element. Let us see how we can do in both the approaches. So, before doing that, we can actually derive the exact solution to this using the strength of materials approach. So, as I said that the problem can be statically reduced to a problem of a cantilever beam with a end moment m as shown in the figure. The moment m needs to be determined from the constitutive law of the PVDF material. So, the beam is under the 1D state of stress with a stress acting in the x direction. So, we have simplified the problem considerably, so that we can actually go ahead and do a simple exact solution, and we will actually check this exact solution with our beam element formulation. So, from the constitutive law, that is the actuator law, we have sigma equal to S times sigma minus S inverse D into E. So, we can write the constitutive law into this form, where E is the piezoelectric coefficient which we have derived it earlier. So, the first part of the above is due to mechanical part, which is 0 in the present case, because there is no mechanical loading we have applied. We have applied only purely the electrical loading, which is converted into equivalent load, that is equivalent moment, and hence the first part is not relevant to the present problem. Since the beam is in 1D state of stress, only sigma xx acts and the bending stress in the axial direction exists. The only material property here of relevance is the Young's modulus y, and the relevant piezoelectric coefficient is E31, that is the piezoelectric coefficient, because it is in the direction 1 due to the field in the direction 3, that is the z direction, which is the first element of the third row of the matrix E. Hence, the constitutive law here becomes sigma xx will be equal to E31 into Ez, or E31 into V by T. V is the applied in the z direction, applied field in the z direction. From the elementary beam theory, we said that m by I will be equal to sigma xx by z. Z is the thickness coordinate. So, where m is the moment being acting on the cross section, and we have found the moment from we need to find this moment to be lumped onto the to be used in the equation, and I is the area of moment of inertia of the cross section, and as I said, z is the thickness coordinate. So, substituting this into the equation, we get basically we take this, the moment is, we substitute sigma x here. So, the m by I will be equal to V into E31 by T by Z, and we get and at the midpoint of the thickness at the two top ends, z ranges from minus t by 2 to plus t by 2. When we substitute this, the moment becomes 2 into E31 V I by T square. So, from the theory of deflection of beams, we can show that the transverse displacement W of a cantilever beam is given by W m due to a cantilever is mx square by 2 EI, with m substituted from E31 coming from the piezoelectric constitutive law. So, when we actually plug this in equation, we get that the equation for a bimorph cantilever, a piezoelectric PVDF beam is given by this equation. So, we can substitute x at any point and we can get the deflection due to this effect of piezoelectricity. So, suppose we take that at x equal to L, that is at the tip, E31 V by E by L by T whole square, we get that. So, we can basically see how this whole thing when we increase the voltage for a given material, there is the deflection increases, or when we decrease the thickness or increase the length, the deflection increases. Next, what we do is we will add, in addition to electric field, we will also introduce a mechanical load P. So, when we do that, now we have two problems, one is due to mechanical load, one is due to electrical field. We have already found out what is the deflection due to electrical field. Now, we will take the mechanical load and we will solve this problem of cantilever beam with a mechanical load L, and we know that this can be easily solved by any of the deflection methods used in strength of materials, and the exact deflection at any point x from here can be got by x cube by 6 into minus x square L by 2 multiplied by P by EI. And when we substitute at x equal to L, so we have taken x equal to here. So when x equal to L, we get the deflection is PL cube by 3 EI. Now the total deflection at the tip is due to mechanical load, which is PL cube by 3 EI, and due to the electrical. So we see that basically the electrical deflection opposes the mechanical deflection. So when we increase the voltage V, it will be increasing, it will decrease the total deflection to such a level that we can actually choose a voltage which will make the total deflection 0, and that is precisely the actuation that we are talking about. So from this expression we see that the voltage is increased, it reduces the net deflection due to mechanical load. So we can actually get an expression that what is the voltage that is necessary to make the deflection 0. So basically we can equate this term equal to 0, and we can get what is V that makes the total deflection equal to 0, and that is given by here. So we can actually make this equal to 0 by using this value of voltage. So it is very clear that the presence of electrical load helps totally eliminate the deflection in a cantilever beam due to the mechanical load. This in essence is the main principle of actuation, which can be exploited to a variety of application, as I talked before. Now let us do the finite element solution. So as I said here, in this lumped approach we need not use any smart or electrical degree of freedom. Here the forces are generated due to electrical field are needed to be lumped onto the corresponding finite element degrees of freedom, which in this case is the moment m, which is given by this expression. Since our objective here is to see how the deflection caused by a pure mechanical load is negated by the electric field generated through PVDF patches, we need to retain the degree of freedom corresponding to the transverse mechanical force at the tip of the cantilever beam. So we go back to the stiffness matrix which we derived in the lecture 28, which will be used here, which is basically yi by L cube. Y is the basically the Young's modulus given by this matrix related to the W1 is the transverse degree of freedom, theta 1 is the slope at the node 1, W2 is the transverse at the node 2, and theta 2 is the rotation at node 2. So we will model this beam only through one element here, and we need first to enforce the boundary conditions. Since it is a cantilever beam we are talking about, so you have W1 equal to theta 1 equal to 0 here. So we apply this and eliminate these two rows and columns, and we will have only these the reduced stiffness matrix will contain only these terms here. So which is written here, P2 and M2 is related to W2 and theta 2 by here, and we know M2 which is got by our reducing the electrical load into equivalent moment, which can be applied here. So we take the inverse of it, W2 theta 2 is the inverse of this matrix which is given here, and we substitute M2 is equal to 2E31 V I by T square, and from which we can compute the transverse displacement, which will be equal to this expression, and when we substitute for moment we get this, which is same as what we got from the exact solution. So because the stiffness matrix for a beam is exact, we are able to get the exactly reproduce the strength of material solution here. And now if you apply a vertical load P here at the transverse degrees of freedom, so we also get that the total solutions can be, so here this will not be 0, in the first case it is 0, but in this case we have a P here, and when we get the total solution is given by this, when we put this equation we get this, and which is same as what we got with the strength of material solution. And again we can equate this to find out what is the total voltage to make the total voltage required to make the total deflection 0. So, what we have seen here is what we derived from the exact solution we are able to reproduce exactly with the finite element solution. Next, let us see whether we can actually do a much sophisticated element formulation, that is in terms of the 2-dimensional 4-noded isoparametric finite element formulation. We discussed isoparametric finite element formulation in lecture number 29, where we outlined the procedures that are required. That is, to recap, we require both the variation of the dependent variable, that is the deformation u and v, and also the variation of the coordinate. In addition, now because we have a smart degrees of freedom, we are not assuming anything with regard to the uncoupling of the sensing and actuation law. We take it as it is. We introduce also a smart degree of freedom into the formulation, and this smart degree of freedom will be only in the z direction. So, we use this. So, the general degree of freedom is shown here. So, you have at each node it can take 3 degrees of freedom, that is the axial deformation u, the transverse deformation v, and the electrical displacement E. And this is mapped onto the rectangular isoparametric coordinate system xi and eta, and using a coordinate transformation. So, the xi and eta which is mapped onto a square of unit 2. So, totally this element will have 12 degrees of freedom. So, now we need to assume the variation for the 2 mechanical degrees of freedom, that is u and v, and u and w here, and the electrical degrees of freedom. The mechanical degrees of freedom is assumed exactly the way we did for the conventional mechanical structure. So, we take it in the form of Ni ui, W is equal to Ni Wi, where ui and Wi are the nodal coordinates of the given element, and xi and eta are the isoparametric coordinate system, as I said, and we write the shape functions in the form of in the isoparametric coordinate system, and these functions which are given here were derived in the lecture number 29. So, now the question is, how do we actually interpolate electrical field, which we have also introduced as additional degrees of freedom. The electrical degrees of freedom is exactly assumed as the variation is assumed exactly same as that of the mechanical degrees of freedom. That is, we take that Ez or the E as a function of xi and eta Ni into Ei, where Ni is again given by these 4 degrees of freedom. We have 4 E's at the 4 nodes. So, that means it will have 4 shape functions. So, here the same shape function is used for mechanical degree of freedom as well as the electrical degree of freedom. The isoparametric formulation, as I said, we map the actual geometry to a square of size 2 using the generalized coordinate system through a Jacobian transformation. So, for which we need to assume the variation of the coordinates, and the coordinates are assumed exactly as that of the mechanical degrees of freedom and the electrical degrees of freedom, because it is an isoparametric formulation where the same number of nodes that participates in the deformation will also participate in the coordinate transformation. So, the Jacobian is computed using a chain rule. I am not going into this. This was explained in lecture number 29. We go because the Jacobian makes the coordinates, the derivative with respect to x is related to derivative with respect to xi and eta. So, once we establish this relation, then we are in a position to evaluate the strain displacement matrix, and the strain displacement matrix, in addition to the mechanical degrees of freedom, we also introduce the electrical degrees of freedom, which has no strain except that it is directly related to the electrical displacement. So, this aspect becomes the strain displacement matrix. So, now using the assumed variation of field variables, in the field variables here are the displacement u, w and the electrical field E, we write the element vector displacement vector as u1 w1, u2 w2, u3 w3, u4 w4, that is the mechanical vector, and the electrical vector is E1, E2, E3, E4 at the 4 nodes. So, now the strain displacement matrix after it is computed will be of this form B into U, and it has two explicit components, one coming from the mechanical degrees of freedom, that is U and W, and one coming from the electrical degrees of freedom E, and the mechanical degree of freedom size is 3 by 8 corresponding to 8 degrees of freedom and the 3 constitutiva, and the electrical degrees of freedom has only 1 constitutiva and it has 4 degrees of freedom. And the expanded form of this B matrix is given by this equation here, where the B matrix will contain only the shape function matrix corresponding to the electrical degrees of freedom. And this part is very similar to that what we derived in the earlier lecture. So, we just directly port it here, and these are filled with zeros, and only this part corresponding to the electrical degrees of freedom gets added to the strain displacement matrix. The next part is, because there are additional complexities that has arisen due to the coupling, we need to rewrite the weak form of the governing equation, and the weak form of the governing equations can be got from the Hamilton's principle, which we actually derived in the earlier lectures. So, here we take the V form and minimize it to get the finite element matrix, just similar to our principle of minimum potential energy. So, the first part is the inertial part due to mechanical degrees of freedom, that is coming from the kinetic energy of the system. This is the strain energy of the system. This is the energy due to, this is the additional energy that comes into picture because of the piezoelectric material, that is coming because of electrical displacement, and this is the force vector due to concentrated load, this is due to the surface traction, and this is the additional force that is coming here. So, here S1 and S2 are the two surfaces where the surface forces and the residual displacement act. Now, using the constitutive model, we can rewrite the weak form of the equations in this form by taking the minimum variation, and here this is coming because of the constitutive model, and we are not deriving it here mainly because it is too complex, but assume that this can be done by taking care of the embedded system as we do it for laminated composite. So, these are the total matrices that are going to come into play because of the constitutive matrix, the weak form of the governing equations. Once we group these things together, we can now in this equation we can substitute the variation u equal to ni ui, then we have w equal to ni wi, and E equal to Ni into Ei. When we substitute this into this equation and write it in matrix form, this is the mass matrix, this is the matrix corresponding to mechanical degrees of freedom, which we call it as KUU. This is due to coupling between mechanical and electrical, which you call it as KUE. This is due to again KUE transpose, and this is due to purely electrical field, which we call it as KEE, and these are the force vector due to concentrated load, surface load, and also the body force due to electrical field. So, we put all these things into matrix form, we get here in this form. We note that there is no entry due to the inertial component coming from electric field, because we still take that it is not an electrodynamic problem where there is a coupling between the dynamics, the inertial force also getting coupled here. Here we say that the mass is only totally due to the mechanical degrees of freedom. So, there is no component of mass that will come into the due to electrical degrees of freedom, and we see that the mechanical degrees of freedom or electrical degrees of freedom are coupled through this matrices. This is the coupling that gives us the actuation or sensing element that we want in the for various applications. So, the above equations is the elemental equilibrium equation, as I said, where the KUE where the MUU, I am sorry, this is the MUU is the mass matrix and the KUU is the corresponding to mechanical degrees of freedom. KUU is the stiffness matrix, KUE is the stiffness matrix due to coupling. I have explained all these things previously, and each one of them can be explicitly written now in the isoparametric form. These are all in terms of dA over the volume, which is dV. dV can be written as T into dA, dA is d xi into d eta multiplied by Jacobian. This is basically equal to dx into dy. So, similarly we have for each one of this, which is equal to dx into dy multiplied by T becomes the volume. So, once we get this, we know the shape functions, we know the density, we know the matrices here by using all these things, and mu33 is the permittivity. Now, we know the complete system of matrices and we are in a position to solve the same problem using the 2-dimensional approach, not the lumped approach which we talked a little bit earlier. So, here the elemental load is due to the mechanical load, concentrated load and the surface load, and QE is the charge vector due to electrical displacement. The matrices in the finite element equations are assembled as in the case of the mechanical structure. We did some examples in the last class, the last lecture, and we find out the global stiffness matrix, then we enforce the boundary conditions and we solve for the displacement and the electric field. Note that it has a 0 diagonal in the block matrix which requires special solution schemes. So, we cannot directly solve because it becomes a positive semi definite system. So, we need special solution schemes. The method of solution sensing and actuation problem are quite different. Now, we will see how we can do a sensing problem or an actuation problem. For a sensing problem, for a given mechanical loading, we need to determine what is the voltage, and this voltage will exhibit certain features which we can extract to do the sensing using a smart patch. So, this is basically done by obtaining the mechanical displacement due to the given mechanical load, which is then used to obtain the electrical field and hence the voltage developed across the sensor patch. As I said, this will introduce certain features and these features can be extracted to actually do a sensing problem. So, in order to solve this, the global matrix equation which is given in the previous case here, this equation we can actually write it as two different equations. We can eliminate this portion for the getting the voltage. For example, this can be rewritten in this form. The first equation can be expanded as given here and the second equations can be expanded like here. Now, from the second equation, because this is a square matrix, we can take an inverse. So, we can take Ke inverse into Q minus Ke inverse into Qe transpose into U. So, we substitute back here and we totally eliminate the electrical degrees of freedom and entirely we leave it as the mechanical degrees of freedom. So, in the above equation is the only in terms of mechanical displacement which can be solved using the conventional solution techniques. So, using this solution we can obtain the electrical field once we know the mechanical through this equation. So, for actuation problem, the voltages and hence the electric field goes as input for the actuate, because we have to feed the electric field in order to actuate. So, that is the second equation in A, that is this equation is not required for the actuation problem. Hence, the equation becomes this equation. So, for actuation problem we have this one and this goes as an input here which is equivalent load, and now we can actually perform the actuation. If any arbitrary value of E is specified, the problems comes under the category of open loop control. If the value of E comes from the sensor input and which is fed back into the controller, then the control scheme is referred to as closed loop. We can do both open loop and closed loop from the finite element analysis, and this is how we do it for the using the two dimensional problem. So, as we see here that this formulation using the isoparametric is a level higher and more sophisticated than the lumped approach we did. The lumped approach only gives us an approximate value how this the piezoelectric material operates, because we make this assumption that the sensor equation, sensor law and the actuation constitutive law are uncoupled. But in actual case, in what we have done in the second approach, we do not use any such assumptions. We take it as it is, then we simplify the equation, and then we can construct the plant matrix or the output matrix which are used for control, for especially for closed loop control from the finite element formulation. Let us now do the numerical example. We will consider the same numerical example which we solve using the exact equation and also using the lump approach. And here we will see how more information can be got, especially for the actuation problem. So, this is the static problem where the effect of mass is neglected. So, we have to show this example, we have modeled this structure only along this plane, xz plane, using 300 2D plane stress finite elements with a thickness T here given here. In the first problem, the voltage is increased from 50 volts to 200 volts. So, when we actually do that from 50 volts to 200 volts, we see that the deflection, we know that when we apply this load, the tip is going to deflect maximum in this direction. So, there is no mechanical load here. So, as we increase the load, we see that the deflection increases as we increase the voltage here. The other one which we have said is, for a given voltage, how does this whole the theoretical tip deflection vary. So, we have given in the form of the deflected shape of a beam and also the graph relating to the voltage versus the tip deflection. So, as the voltage increases, we see that the tip deflection increases. So, now let us actually do some case studies using the formulated element. So, here what we have done here is to show how the piezoelectric material can be used as a sensor now. What we did is the actuation problem. We actually used to actually see how we can make the deflection 0, but here how we can actually sense the presence of the crack. What happens when the piezoelectric material is put on a cracked beam. So, here we have taken a composite beam where the crack is in the form of delamination. Composite is constructed as a laminate construction, and due to excessive loading the laminate can peel off, causing delamination. So, is it possible to actually determine predict this delamination well in advance? That is the goal, and for which can we use this piezoelectric material. So, here the delamination essentially behaves as a stable crack and can be characterized what is known as in fracture mechanics called the strain energy release rate. The main objective here is to understand the distributed sensing behavior of the piezoelectric sensor patches embedded in a composite with a growing delamination. So, in the composite there are 3 modes of failures, whether it is in composite or metal. One is the opening mode where the crack opens, this is called the mode 1 crack. When in the other one is when the mode shears due to a shear loading, which is opposite, put in other terms it shears. So, that is called the mode 2. One is the out of plane loading, that is the tearing out one against the other, which is called the mode 3, and the crack is characterized by the basically the stress intensity factor. So, here what we have done is we have taken a cantilever beam with a central delamination through width, and we want to see what is the piezoelectric sensor response, that is what is the voltage that is developed as the crack starts propagating and goes inwards. What would be the sensor voltage that will be predicted in these 3 cracks, which is very useful to actually see whether there is something going on. So, hence the objective is to study the generated voltage in the sensors to the approaching crack tip stress fields, and to study the sensitivity of this defined by the J integral, which is a measure of the crack sensitivity or the stress intensity factor with the voltage generated by the sensor patch. So, this is basically used in structural health monitoring study. So, here we have not defined what it is just a case study to make us understand how this can be used in the sensing applications. So, if you before doing it, if we model this with our formulated element and predict the stresses, this is the basically the axial stresses, and we see that there is a very high stress is found in this region, which is basically a singular region where the stresses will be very high because the crack is emanating from here. So, we can actually predict the sigma x, sigma z, which is the other stress that is there, which is also pretty high here, and the tau xy basically. So, when we actually study the voltage here under the static load, so this is the length of the delamination, which is increased from 20 to 50. The 20 is very small, it approaches 50, which is very near to the top and the bottom sensor, and also the sensor right across the crack tip. So, we see that the voltage increases as the delamination increases at the location from the surface node. Okay. And this is basically the voltages that is found, and we see that this is on the first sensor, this is the tip sensor. So, we have 3 sensors here. So, basically this is the crack here, the sensor here, and sensor here. So, this is on the top node, this is a front sensor response, this is the bottom sensor response, and this is the response at the approaching. You see there is a sudden peak of the stresses. So, based on the increase in voltage, the state of stress changing, and based on this concept we can basically say that the crack is there which is approaching fast, and that is possible, that was made possible only because we had the piezoelectric patch here. So, this is very tremendous for us for in terms of using this for the sensing application. This is one of the sensing applications. There are many applications that we can actually construct using the piezoelectric material. So, here we clearly see there is an increased peak in the response in the sensor 3, and based on that we can basically say that there is something happening. Even here in the front sensor we see that as the load is increased, as the delamination nears 50, there is a huge increase in the load. So, this is the sensitivity of the J integral. So, basically what we are saying is, if we just measure the voltage and if we have this curve, we can say how severe the crack is and is there any necessary repairs that we need to do to avoid catastrophic failure, which is very, very important from the structural health monitoring. So, this was done basically by using a load which was in this direction. So, now we do the same thing when the load is in this direction where we apply here. So, this is going to cause a shearing. So, the shearing is basically the mode 2 load. So, in the shearing load, here is the sensitivity of the response. You see there is a tremendous increase in the voltage when this is approaching very near the crack tip. So, this is on this sensor here. So, basically by measuring this we will know that whether the approaching is it going to be catastrophic or not. So, we can actually generate a lot of this curve and correlate our the fracture parameters with the sensor voltage. This is basically the voltage distribution across the sensor surface for a very delamination length. So, we see that it increases tremendously as the length of the delamination is increased. So, we have shown that we can basically use this concept of sensing using piezoelectric for structural health monitoring applications. We can again do this for variety of other applications. So, this is another way where the sensitivity is done, where for the patch in the upper portion of this sensor here, and the same thing is the voltage distribution. This is the sensitivity. So, we see how the voltage, in most cases there is a linear variation. In some cases where the level of stresses are very high, especially in this sensor, we see a significant nonlinear variation. So, basically what we are trying to see here is how we can use piezoelectric material for the sensing applications. This is another aspect of in the lower sensor. So, we have done for the in this sensor, this you see there is complete nonlinearity, especially for the mode 2 loading, how we can the voltage varies. So, basically this change in voltage variation is a measure of the state of stress in the happening in the laminate, which can basically be used to actually make an opinion about how severe the crack is, and that is basically a sensing problem. So, let us summarize what we studied here. So, in this lecture we covered the following. We introduced the piezoelectric material constitutive model and discussed its effect on the FE modeling. So, basically the effect is coming in terms of the additional coupling matrices, because additional energy that goes into the weak form of the equation due to piezoelectric material coming from the electrical field. We developed two different finite element model, one based on beam modeling, where the explicit coupling between the electrical and mechanical degree of freedom was ignored. So, we basically reduced the problem into a statically equivalent load lumped down to the beam model, and we studied that as the actuation problem. So, in the second model we developed a 2D 4 noded isoparametric plane stress model with additional degree of freedom in the form of electrical field. And we also again studied the same actuation problem, that is giving a voltage and trying to reducing the total deflection in the beam structure. Then we introduced another case study how this can be used as a sensing, where we actually showed how this can be embedded into a composite and measure the voltage because of the ensuing mechanical load, and tell about the state of the structure, especially with regard to the presence of crack. So, basically we can use the piezoelectric material as the crack sensor for sensing application. So, essentially what we have covered in the entire finite element method is, we basically said we started basically on how the finite element modeling can be helped in the microsystem design. Then we covered the basic theoretical basis for finite elements, and we basically said how a second order system can be characterized, how many numerical methods can be characterized using weighted residual method, and how we can derive finite element method from the weighted residual method. Then we actually established the theoretical basis of the entire finite element modeling per se, using the mechanical system as the example. This method is not related to mechanical alone. It depends upon the governing differential equation and the physics based on the governing differential equation, and the degree of freedom is basically based on what the physics modeling. Suppose you are modeling a Maxwell's equation, instead of the displacement you would have electric field and the magnetic field as basic unknowns. Otherwise, if you have an electrical, the corresponding forces would be the electrical displacement and the magnetic flux. If you are modeling a thermal problem, then the temperature and the temperature flux will be the dependent and the force variable. So, like that, any physics of the problem we can actually use it. If we are solving a fluid problem, we need to idealize the whole Navier-Stokes equation into finite element modeling, where instead of displacement we will have velocities as the basic degree of freedom. So, it depends upon the physics what you are modeling. So, in microsystem we need the modeling of electromagnetics, electrical field, electrostatics, where Maxwell's equations need to be modeled, wave equation for mechanical system, Navier-Stokes equation for the basically the fluid system, and the Fourier law for the thermal systems. So, it does not matter what the governing equation, the approach what we have derived is exactly same, only the dependent variable meaning is changing. So, in short, The finite element modeling what we have developed can be exploited for all other domains which are prevalent in the smart and micro systems. Thank you.